Calculus is AP Calculus Lesson 4-1, Tangent Line Equations. So we are on our new unit, of course. Here's our unit guide. We have 9 lessons, 2 self-checks, well a total of 4, 2 days of self-checks. Just like normal, that doesn't change until I think Unit 6. So, point slope form. It was important, thank you Gio. It was important in Algebra 1, it was important in Algebra 2. It is very, very important in calculus because this is the fastest way to write a linear equation. Again, linear meaning a line and equation being the equation of that line. So if you're given the point, and that point is 3, 2, what they have given you is xy information. So they've given you the x coordinate, they've given you the y coordinate in that information. If they've told you that the slope is 5, they have really told you that the derivative at the point 3, at the x coordinate 3, is 5. So you can say f prime of 3 is 5. They've given you that information. I should pause that or silence that as well. So by giving these 3 pieces of information, you should be able to write the equation of the line using point slope form. How many of us remember point slope form?
Isn't it y minus y1 equals slope times x minus x1?
You remember all of it. So yes, so y minus, what's y1 going to be? I guess if this is going to be y1, this is going to be x1. So y minus 2 is equal to, Ben has it. Anyone else? 5 times the quantity of x minus 3 and the quantity, there it is. Super fast way of writing it. This way is nice because they will always be giving you points and they will always be giving you equations that you can find the derivative of. So once you have the points and you have the derivative, this is the fastest way of doing it on the AP test. That's the way I'm going to be doing it for the rest of the year. No more y equals mx plus b stuff. This is always going to be this equation. And the equation that you need to memorize, as Ben has memorized it, is as follows. I'm going to do this in red. It is important. It is starred. Remember this for the rest of the year. Maybe the rest of your lives. I don't know. Y minus box. I'm going to say that's going to be our y1 is equal to, I do boxes because that lets you know, oh, I need to find something there. It's blank. I need to fill it in. Is equal to box. We need to find the slope times the quantity of x minus box. And the things that go in each of those boxes, this is going to be y1 if we're going to be using that. But really, you're usually just going to be finding the y coordinate. I'll just write y1 for now because that's what Ben gave us. F prime, the derivative of f at that position, and x1. Those are the things that go into the boxes. Those are the 3 pieces of information you need to find. Plug them into this equation. You have the slope of a line. All right, so why do we need lines? We're talking about calculus. We're talking about curves. The reason is because this is the best first step to approximating a curve. So if I have some curve, I can, and I know the position here, and I want to find where it is out here. You can use this line. You can see that right here, they're still really darn close to each other. So if I use a line to approximate where the height is of the curve, it's going to be a pretty darn close approximation. The farther away that you get from your original point, the farther or the more error you're going to accumulate. So for really close approximations, thumbs up. Line is okay. But for other approximations, not so well, for farther away. So this is what I want to say. Let's go ahead and say that the x coordinate of this point is 1. Let's say that the height of that point, let's call it 2. And I'm going to tell us that the slope in red here of this line, the slope m, is going to be 3. With that information, let's practice again. What is the equation of this line at line tangent to the curve at x equals 1? Ben knows how to do it, so I want to hear from either Arrow or Rochelle or both. 3 times the quantity of x minus 1. There it is. We can use that line to approximate any point that's close to 1. Anything close to that x coordinate. So I just want to make sure that you understand where each of these is coming from. If it feels like I'm kicking a dead horse, then that makes me proud because you already know this and you're going to destroy this on the test and all the self-checks. That position was the y-coordinate. That position was f prime at the x-coordinate of 1, and that 1 came from the x-coordinate. We know where all of those came from. By the way, I want to make a little note over here. There's another way of giving you the x and y coordinate instead of just giving it to you on the graph. Sometimes they go like this. This is an optional form, and AP creators love this form. So I would say like 75% of the time, if they give you an x and y coordinate, they're going to give it to you like this. This form is going to look like this. F of 1 is equal to 2. That gives you the x coordinate here, the y coordinate here.
Wouldn't 2 be the slope?
It would be the slope if it was f prime of 1. So I can write that off to the side too if you want. F prime of 1 was equal to the slope. That was 3. That's the one that will give you the x and y coordinate. And usually you'll have to do math to figure out the slope on your own. We'll see an example like that on the backside, but we're not there yet. I need to talk about overestimating versus underestimating with a line. Usually these types of questions come up on multiple choice and free response. Is your approximation using that line an underestimate or an overestimate? So let's go ahead and draw 2 lines on the left-hand graph and 2 lines on the right-hand graph, a total of 4 lines. Let's draw a line that's tangent to some point on the left. I'm doing my line over there. Let's do some line over here that's tangent over here. Regardless of if the line is increasing or decreasing for the slope, you can always tell if it's an underestimate or overestimate. So the point that you're actually looking at is the point of tangency, so we'll make a little black dot. If I'm looking at the line on the left over here, if I'm estimating using this point, this is the point that I'm actually getting, but I really wanted this point on the blue line. So was this point right here an overestimate or an underestimate? This orange point. It was an overestimate because I'm over the blue line. What about over here on the left-hand side, even more left? Is this an overestimate or an underestimate?
Over?
It's an over again. Yeah, I'm going to hear from Arrow or Ben on this case. On this other tangent line that we've drawn, is this point an overestimate or an underestimate?
Still an overestimate.
Still an over. And Arrow, what about this point right here?
Also an overestimate.
Everything here, I agree, is an overestimate. So that's really key. Everything on this graph is overestimate.
So if it's concave down, then it's always overestimate.
That is the key. Overestimate if f double prime, oh, come on, lag, f double prime is greater than 0. If it's, sorry, oh, that was totally backwards. If f double prime is less than 0. If it's concave down, it's always, always, always going to be an overestimate. We saw 4 points of that. And what do you think about here? If you had to just take a guess for the right-hand side graph.
Underestimate if f double prime is less than 0?
Yep.
Greater than 0.
If f double prime, if the concavity is concave up, greater than 0. And that's true. And we can just do 1 quick line or 2 quick lines if you want to just show that. So there is my, why is it snapping? If I hold Option, there, it gets rid of it. 1 line right there, 1 line right there. So if I just very quickly do that sketch where that's my point of tangency, that's my point of tangency, you can see that each of these, no matter where on this red line, as long as it's not actually on the point of tangency, each of these orange points is an underestimate. Each of those orange points is underneath the blue line. So that's key. I guess I should have done a red star there because that comes up over and over again. They love asking those questions, and now you know. All you have to do is check the concavity. You don't have to check the slope of the line. You don't need to check the height of the points. You only need to check the concavity of the original function that you're trying to estimate for. All right, let's see an actual example. This one is very, very close to an AP question for free response. They will modify it slightly for multiple choice. All right, so they give you an equation. There's your equation. F of x is equal to 5x squared. I need to find the equation of the line tangent. Pause. I'm going to pause right here. and use it to approximate the value of f of 1.1. We'll do that after we find the equation. So let's pause right here. For the equation above, find the equation of the line tangent at x equals 1. How am I going to do that? Just we have to find the line tangent. So we're finding one of these red lines here, one of the green lines here. I need to find one of those for this curve. This is a quadratic. I need to find that tangent line. So how am I going to do that? I need pieces of information. As soon as you see line tangent, you know you're going to be using that slope-intercept form, the point slope form. So let's go ahead and write that down. Arrow, do you remember it?
Just the normal
Point slope form, so it's y, I want the boxes and stuff.
y minus y1 equals
X minus x1, there it is, cool. So we know that we have 3 pieces of information to find. Do we have any of that information already?
we do have that.
Ah, we have the x, so that goes right here. Boom. That's our x coordinate, x1. All right. Do we have any other information?
Yeah, well, we kind of have the y.
Sort of. We can find that really easily, though, right? How do we find our y coordinate?
Plug in the x.
Yeah, just plug it into the equation. So to find y1, y1 is going to be equal to 5 times the quantity, 5 times the quantity of 1. We're plugging in 1, and we're going to square it. So 1 squared is 1, times 5 is 5. So that's going to just be equal to 5. Plug it in. So far, so good. Easy peasy. Now let's work on this part. Let's work on f prime at 1. I need to find f prime first. By writing out this equation as your first step, you know exactly what you need to do. It tells you, okay, we are missing f prime of 1, so I need to find f prime of x. I need to take the derivative. If I take the derivative of f of x, I get what? Anyone?
10x.
10x. And then I need to find f prime of 1, so I need to plug in 1 into that equation. That's 10 times 1, that's just 10. So there it is, 10. All right, we did the first part. The first part up to here, find the equation of the line tangent at x equals 1. Done. Now that we have this beautiful equation, we're going to use it to approximate f of 1.1. So I'm going to rewrite this full equation now down here. Y minus 5 is equal to 10 times the quantity of, and I'm going to leave the x blank, x minus 1. Because now instead of using 1, we're going to use 1.1 for our x value. So I'm going to plug in 1.1 as my new value. And I'm going to evaluate this thing. What is y? What is the height? So when I do that, 1.1 minus 1, shout it out. Yep, so this whole thing right here is just 0.1. 0.1 times 10, 1. So we now have y minus 5 is equal to 1. I have to add 5 to both sides. Y is equal to, there it is. And we can see how close that was too. So if I actually plug in 1.1 here, I'll have 1.1 squared, which is 1.21, times 5, which is 6.05. The actual value was 6.05. Our estimate using the line tangent was 6. Pretty darn close. Pretty cool. All right, that concludes the notes. Are there any questions?
When is this actually useful?
It's useful for approximating things, especially on higher levels. So when you get into higher levels of math, they'll say, oh yeah, you have a curve, you have a quadratic. Yeah, you're going to have to do a linear approximation, which means you have to boil it down into a line. Linear algebra is great until you talk about things that are not linear all of a sudden. So you learn processes of boiling things down into linear equations. So they're nice to handle, like the stuff up here. Although when you do linear math, it becomes a lot harder, but it follows basic rules. So boiling things down into a linear case is the same case for a bunch of higher level math, although it is still slightly more complex than this. So this idea of boiling it down is important. Yeah, that was a good question. Any other questions? All right, that concludes the notes.